here we are doing, if v1, v2 till vn are in V, then either they are linearly independent or some vk is a linear combination of the preceding ones. Okay, so here we are in this theorem means either this set are linearly independent, or if they are not linearly independent, they should be linearly dependent. So at least one scalar means one vector from here can be written as a linear combination of the preceding ones. So if I take this, if these are linearly independent, so there is nothing to prove, means there are nothing to prove. Suppose that these vectors, suppose that we are taking the linear combination here, which is equal to 0, where not all alphas are 0. So we take that this set v1, v2 till vn are linearly dependent. So here all the alphas are not 0. Okay, so we are taking k to be the largest integer, means k is the largest integer for which alpha k is not 0. Okay, k is the largest integer for which alpha k is not 0. And since also we are taking here all the alpha i's which is bigger than k will be zeros. Okay, for I greater than 0. So we take the linear combination here with the vectors. So we have alpha 1 v1 plus alpha 2 v2 plus so on, alpha k vk plus alpha k plus 1 vk plus 1 plus so on, plus alpha and vn. So this is greater than k. This all the scalars above this will be 0. Okay, so this we are by using this we get alpha I equal to 0 for I greater than k. So we have here alpha 1 v1 plus alpha 2 v2 plus alpha k vk is equal to 0. Now we are taking here this alpha k is not 0. So these vectors I bring this side, so I get this. Since alpha k is not 0, I can divide throughout with alpha k. So if I divide throughout with alpha k, I get vk to be this. That shows this vk is a linear combination of v1, v2 till vk minus 1. So hence we have proved that vk is a linear combination of its preceders. Okay, so that is our theorem, hence the theorem. And the remark 2 says that here we have vectors v1, v1, v2 till vn in V. And W as a linear spans, okay, W spans this vector. If v1, v2, vk are linearly independent, okay, so if we are having this set is linearly independent, then we can find a subset v1 till vn of which forms that consists which of the form this consisting of linearly independent elements whose linear span is also W. Okay, so that means here is like this. Suppose these are, I'm taking this is your set. Okay, so I'm taking some vectors from here. So this I collect some vectors from here, that is v1, v2, v3, so on till vn. So I'm collecting this, but this set is not linearly independent. Okay, this set is not linearly independent, but they have given you that the set from here only I'll collect only those elements which are linearly independent with each other. So v1, v2 till vk is also linearly independent. Okay, which is also linearly independent, then which is also linearly independent. Okay, this set is already is linearly independent. Okay, then we can collect some elements from here, we can collect some vectors from here. Okay, we can collect some vectors from here. Suppose I collect vi1, vi2 till vir. This is also linearly independent. So I'm collecting from here. So I can search some vectors from here which is linearly independent. So if I combine this together, v1, v2 till vk and vi1, vi2, so until vir, then this set is also linearly independent. Okay, this set will be also linearly independent and this will be capable to span W also. So that is our remark 2. The remark, second remark here, if V is a finite dimension vector space, okay, so if we take V to be a finite dimension vector space, then it contains a finite set V1, V2 till Vn of linearly independent elements whose linear span is V. We can find always, if V is a finite dimension vector space, we can find a finite set this, which is linearly independent and which will be capable of spanning the whole vector space. Okay, we can always find that this remark is like this. Suppose this is your V. Okay, this is your vector space V. I can find one small set here, V1, V2, so on till Vn. We can collect those elements, those vectors from here. We can collect from this V, those vectors. Okay, we are just collecting the vectors from V. We are just collecting those vectors from V. We can always find vectors from V which is linearly independent. It's linearly independent, and these vectors will be capable of spanning the whole vector space. So that means if we take any vector in V, then it can be written as a linear combination of this. Okay, so that is the remark 2. So we are going to do one more question here related to linearly dependent. So determine the value of A for which the vectors 1, A1, A10, and 0, 1A are linearly dependent in R3. Okay, so we are taking a linearly dependent vectors here. So here we take, let E1 to be this 0, 1A, and E2 I take as 1A1, and E3 I take as this are linearly dependent. So the one can be written as a linear combination of the other two. So I take two scalars alpha and beta such that. So here I take this. Okay, so this one. I take this linear combination. So first vector will be equal to first, second will be equal to second, third will be equal to third. So we get alpha equal to A. Now in the this, I put alpha to be A. So I can take A common, I get A 1 plus beta equal to 0. So A is 0 or beta is equal to minus 1. If I put here, then I get A squared plus beta is equal to 1. So beta I have already found, it is minus 1. So this you transfer here, we get 2. So this implies A is equal to root 2, or that's why A can be written as plus minus root 2. Okay, so the value of A is either 0 or plus minus root 2. Thank you.